All right, let's get into it. Today, we're putting on our detective hats because we're diving into a world of hidden clues and secret patterns. The case we're cracking? It's called unsupervised learning, and these are the ultimate data detectives.
So let's set the scene. Imagine a gigantic library where none of the books have titles or covers, and they're all just thrown in a massive pile. That's basically our digital world. We are creating an absolutely staggering amount of information every single second. But most of it, it's completely raw, totally unlabeled. It's a sea of data without a map.
But here's the thing. Just like an unsolved mystery, all that chaos is packed with clues. What if we could find the hidden stories, the secret connections, the really valuable insights that are just buried in all that noise? What secrets are hiding in plain sight, just waiting for the right detective to come along?
And that brings us to the heart of our investigation, the unlabeled data mystery. We're facing this mountain of evidence, but we have zero instructions. There are no answers in the back of the book. Our job is to find the story that's hidden deep inside. So how in the world do you crack a case like this? Well, you need a special kind of investigator, a tool that's designed to find patterns where, honestly, none seem to exist. And this brings us to our lead detective, unsupervised learning. Let's figure out what it's all about.
So what's the deal with this detective agency? Well, unlike its famous cousin, supervised learning, which gets a cheat sheet with all the answers, unsupervised learning gets thrown into the mystery completely cold. No labels, no predefined categories. Its entire job is to stare at all that raw data and find the underlying structure all by itself. It's about discovering the plot, not just following it.
Of course, every great detective has a toolkit, and unsupervised learning is no exception. It really relies on two super powerful techniques to solve these data mysteries. Let's take a look at what they are.
Okay, so the toolkit has two main instruments. On one hand, you have clustering. This is like building a classic suspect board, right? You're grouping all the similar pieces of evidence or data points together to see who belongs with whom. And on the other hand, you've got dimensionality reduction. Think of this as cleaning up a really messy crime scene, getting rid of all the distracting noise and junk so you can focus on the clues that actually matter.
All right, now let's meet some of the star detectives in this agency. We're going to see exactly how these specific algorithms work their magic on the data.
First up, we've got a real classic, the methodical organizer of the group, Detective K-Means. This algorithm is super popular because it's fast, it's efficient, and it is great at just sorting messy data into nice, neat piles. And you can see just how logical its process is. It all starts with step 1. You, the chief investigator, have to decide how many groups, or K, you're looking for. Then, in step 2, it randomly drops some starting points, called centroids. Think of these as the first headquarters for each group. And then it just loops. Step 3, assign every single data point to whichever headquarters is closest. Step 4, find the new center of those groups and move the headquarters. And step 5, you just keep repeating that until the groups don't change anymore. It's simple, but so effective. But, like any detective, K-Means has its pros and cons. It's incredibly fast and it scales really well to huge data sets. But its biggest weakness, you have to tell it exactly how many groups to look for right from the start. And a single odd piece of evidence, an outlier, can totally throw off the whole investigation. So for those pesky outliers that can mess up K-Means, we call in a specialist. Meet DBSCAN, our density-based detective, the resident outlier hunter. This algorithm couldn't care less about a preset number of groups. It only cares about how tightly packed the evidence is. And this quote right here, this is its whole philosophy. DBSCAN looks for crowded neighborhoods of data. If a point is in a dense area, boom, it's part of a cluster. But what if it's all alone, way out in the middle of nowhere? DBSCAN is smart enough to just label it as noise and ignore it. This makes it amazing for finding weirdly shaped groups and spotting anomalies. So, we've talked a lot about grouping the evidence. But what happens when there's just too much evidence to even begin with? For that, we call in a totally different kind of specialist, Principal Component Analysis, or PCA. This is our signal finder. Imagine a case with thousands of variables. It's like a crime scene with thousands of irrelevant details, fingerprints, footprints, weather reports, random witness statements. It's just overwhelming. Most of it is just noise, and it's hiding the real story.
And this is where PCA just shines. It analyzes all of those variables and boils them down into just a few new, powerful variables called principal components. It basically finds the stuff that's actually important. It filters out the noise to amplify the real signal, making the hidden patterns suddenly crystal clear.
So look, the most important thing is knowing which detective to call for which case. K-Means is your go-to for straightforward jobs like customer segmentation, DBSCAN is perfect for hunting down fraud or anomalies, and PCA is the absolute master of simplifying complex data like compressing images or reducing noise. Each one has a job and each one has its limits.
Now, this isn't just theory, okay? These data detectives are out in the real world solving critical cases every single day. Let's look at some of their actual case files. Think about it. When a website groups you with other shoppers who have similar tastes, that's K-Means solving the case of the similar shoppers. When your bank flags a weird transaction and texts you, that's DBSCAN on the case of the unusual transaction. And in medicine, these algorithms are grouping genes to help researchers understand incredibly complex diseases. These detectives are absolutely everywhere. But, the work of a data detective is never truly done. For all the incredible cases they've already solved, there are still some huge, fundamental mysteries that the entire field is trying to crack.
And these are the really tough questions. I mean, without an answer key, how do we really know if an algorithm did a good job? How do we pick the right number of groups to even look for? And maybe the biggest question of all, even when we find a pattern, what does it actually mean in the real world? These are the unsolved cases that are driving all the new innovation.
And that leaves us with one final, kind of mind-bending thought. We've built these incredible data detectives that can sift through utter chaos and find connections that no human might ever spot. They see the world differently than we do. So the ultimate question is, what else is out there, hidden in the data that we haven't even thought to ask about? What will they discover next?